So let me speak about a problem we are studying since maybe 1 or 2 years. Indeed, the results I will present here are obtained in collaboration with Antonio Azzolini and Alessio Pomponio, and in another paper with Professor Zissu Liu from China. Just to introduce a little bit the system, let me show you what is the origin of the system we want to study, which is the following. Basically, we have a Lagrangian. Well, this is the Lagrangian of the Schrödinger equation. C is the wave function, a complex function. And of course, the Euler-Lagrange equation of this Lagrangian is the well-known Schrödinger equation, which is a complex equation. G prime is a nonlinearity. Actually, we want to study a system instead of a single equation. And in this system, we take into account the fact that our function, our wave function, our particle is interacting with an electromagnetic field, which is basically the electromagnetic field generated by the motion of this particle. This is done in mathematics by means of a power theory, which is the Abelian gauge theory, where one introduces some covariant derivative, makes some tricks, and by tricks I mean you have to substitute some operator with other. You see here the partial derivative with an operator which involves also the gauge potential phi and A of the electromagnetic field. At the end, you obtain a Lagrangian, so-called Lagrangian of the interaction, in some sense, which can be written in this way. For example, you can write psi in polar form, so by introducing two independent variables, u, which is the modulus of psi, and s, which is the phase, and you have a Lagrangian which depends on us, phi, and a. Okay, this is the Lagrangian obtained by means of this covariant derivative. But actually, this is not the total Lagrangian of the system, because you need to add also the Lagrangian of the electromagnetic field, because it is an unknown of our problem. Is here that commonly people uses the Lagrangian of the Maxwell Lagrangian of the classical electromagnetic field, which is the following one: A squared minus B squared. Okay, this is a good model. In this sense, you have a total Lagrangian, which is the sum of the two Lagrangian. And when you write the Euler-Lagrange equation of this total Lagrangian, and you are in a very specific situation, I mean, u that depends just on x, s, which is the phase, which is just omega t, so a very specific dependence of the wave function from x and t. And when you are also in a very specific situation where the potential vector A is 0 and phi, which is the scalar potential, just depend on x, you have a system which is made by these two elliptic equations. And of course, this is called Schrödinger-Poisson system because it is a Schrödinger equation, the first one, and the second is a Poisson equation for the potential phi. Of course, Laplacian of phi, this means that phi is the potential generated by u squared, because it is on the right-hand side of the second equation. This kind of system obtained in this way is the second equation is solved by a convolution with a very known function, the fundamental solution of the Laplacian, right? Which is 1 over x, which has well-known properties, it is well behaved. For example, it is homogeneous, so you can make a lot of change of variables. You can use a lot of curves to course of type, when you make a rescaling in the variable, because k fundamental solution is homogeneous. So in some sense is good to work with this equation. And of course, many of you also have studied this kind of system. There is a huge literature on this Schrödinger-Poisson or Schrödinger-Maxwell system. However, there is a small thing which is the following when you use the Maxwell equations. The fact is that if we compute the energy of the electrostatic field generated by a point charge located in zero, so we have an equation of type minus Laplacian of phi equal to a delta, a Dirac. Okay, the solution is the fundamental solution of the Laplacian. This means that the energy of the electromagnetic field, which is just the integral of the modulus of A squared, is the gradient of phi of the solution. But if you compute this is plus infinity, the fact is that this phi is not in the space D1, 2, the homogeneous Sobolev space. So we have a situation in which a very simple model, a very simple case where the energy is plus infinity. So this is called the infinity problem in the theory of the Maxwell equation. Okay, you may say, however, that this is a very ideal example because we have a charged particle, which is something mathematics. But the fact is that and L1 source, so a density of charge which is in L1, and it can have something similar. And then there is a famous example, which is this one. Take a charge density rho, which is this function here, and you have an equation minus Laplacian of phi equal to this rho. This rho is in L1 in the whole space, so it is a good density of charge because it's the integral, which is the total charge is finite in the space. This function is not in this particular space, Lebesgue space L of 6/5. And in fact, this equation has not radial solution in D12. That is what you want. You want that a solution of this equation is which has an L1 density. Everything is radial, and you want a radial solution with finite energy. But it is easy to see that if you look at radial solution, they are not in. In the years, many attempts have been done in order to circumvent this problem. And one of them is start from the following fact. I mean, as in classical mechanics, okay, you have the Lagrangian of the Newton, which is 1/2m velocity to power 2. You can pass to the relativistic mechanics, so introducing the Lagrangian of Einstein, which is the following one, with that factor, that relativistic factor, that square root of, etc. We can do something also for the Lagrangian of the electromagnetic field. And in fact, this was done by Born-Infeld in the last century, where they basically consider this Lagrangian, which is a very simple in some sense, that it is invariant by the Poincaré group. And also, if you take a first order approximation of in epsilon, you have exactly the Lagrangian of Maxwell. So in some sense, this is a better Lagrangian than the Maxwell one. And the fact is that now you do not have anymore the problem of the infinity problem. Now, if you consider the total Lagrangian and very particular solution, you have a system of this type, which is basically the system we want to address now here. So we have again a Schrödinger equation above, and below there is some divergence equation. So there is also however variational structure for this problem. Of course, the second equation is bad, so we do not have good properties for the fundamental solution of the second equation. However, as I have said, there is a variational formulation. You can find the functional of two variables, which is well defined on the right space, of course. H1, U, for example, in H1, phi in some other space where everything is well defined. The functional is regular. And the fact is that we want to pass to a functional of one variable, because this is a function of two variables. Indeed, it is very, very, very bad. But there is a little problem here, which is the following. The second equation, which is this one, it can be solved if U is in H1, but is also radial. Then the solution is can be found, which is in the right space. It is radial, of course. However, this solution has not the homogeneity properties of the like in the Maxwell case. So in the computations, I mean, we need to use other advices. We cannot use rescaling in some sense. And the fact is that the solution of this problem, of this equation, can be found as a minimum of this functional, but okay, it is easy to see that this functional as a unique critical, a unique minimum. And the fact is that in general, it is not clear that the minimum is a solution of that equation. This happens, for example, if we are in the radial case. So in our setting, this is good, because the minimum of this functional is characterized as a solution of that equation. Of course, this solution has some good properties. For example, it is positive, where the gradient is equal to 1, which is not so good for us. This is something which has a measure which is 0. So okay, the function is some LP spaces. There are also some properties, inequalities that, of course, are used along the proofs. There is also a nice convergence in the last point. Convergence in LP of U gives a convergence in L infinity of the unique solution. So in the supremum norm, which is always something good. And okay, you can define a functional I, which is f of u and phi of u. Now the expression of I is the following one. And okay, the critical points of I are related to the solutions of this equation. In H1 radial, which is a good case for us. However, this is a natural constant, so we are not losing too much working in H1 radial. So the first result I want to present is that for this equation, okay, I'm considering an homogeneous nonlinearity, pure power nonlinearity. If P is in this range, and look at the range, it is not 2, 6, the problem has a ground state solution. Okay, it is a classical solution, I mean, and it minimizes the energy of the functional f. Just to give the idea of the proof, I will not enter in details, but we use the monotonicity trick of Jean-Jean. So we need to write a functional which depends on lambda, and then to show that there is a mountain pass structure in some sense, which does not depend on lambda. And the conclusion is that there is a bounded PS sequence for almost every values of lambda. And then, okay, try to obtain a solution for our problem. And the fact is that the study is done in this way. You consider this equation by adding this lambda. Of course, you want that you want solution whenever lambda tends to 1, because when lambda is 1, we have our equation. And this can be done because we can write our functional in the assumptions of of this proposition, just define A in the, in fact, you see that you can estimate the functional by using simple inequality, embedding other inequalities. But at the end, we estimate the gradient of phi of u in L2 exactly by using the star inequality. And we see that if P is chosen between 7/2 and 6, this functional becomes negative. We have the geometry of Jean-Jean, of the monotonicity trick, uniformly in lambda, and then the remaining is basically standard, because now for any lambda, for almost every lambda, we have Palais-Mail sequences which are bounded, so we have solutions u lambda. Okay, you take lambda which tends to 1, so we have solutions u lambda n for the problem with the parameter in the right-hand side, which is lambda n. And actually these solutions u lambda n are is a bounded sequence which converges actually to a critical point of the functional, of the original functional, our functional. These critical points in some u star. Okay, I do not know if this solution u star is a minimum, is a ground state, but you can see that we can minimize the functional over S, which is the set of all the possible solutions, which is non-empty because U star is there. So once you minimize the functional over S, I mean, it is possible to minimize and obtain a minimum. So this was the case, at least whenever P was greater than 7/2, where we used that star inequality with that power, that exponent Q. How to treat the case whenever P is less than 7/2? Of course, we need to change something in our computation because our method does not work. And indeed, the fact here is to perturb the equation in a different way, this time by adding some terms in the equation. And the terms are the red ones. So I'm adding something to the right and something to the left-hand side, of course, combined in a suitable way. And of course, what I want is now that lambda has to go to 0. So find solutions and show that everything is maintained whenever lambda goes to 0 this time. Okay, Q has to be chosen in a particular way in that interval, maximum between P plus 1 and 4 and 6. The fact is that choosing this perturbation in the equation, this combined perturbation to the left and right hand side, we are able to prove our geometry, our obtain solutions. In fact, now the functional is, okay, the old functional plus some red part. Of course, when lambda is 0, we have our functional. And what happens is that everything works because we have uniformly estimate with respect to lambda. So we have a mountain pass geometry, uniform in lambda. Also the critical levels, which depends on lambda, are controlled and they are not going to 0. They are converged so to some C star. The functional perturbed with the lambda satisfies the Palais-Mail condition. We have solutions which depend on lambda. And this family of solutions, U lambda, actually is a bounded Palais-Mail sequence for the original function. I mean, for the functional whenever lambda is 0, which is our equation. So again, we have a solution to some level. And again, as before, we show that we can minimize and obtain, again, a ground state solution for the system. So the theorem is the following. Whenever P is less than 7/2, but greater than 3, we have, again, a classical solution, which is radial and of minimal energy for the problem, obtained by perturbing in this different way the equation. Of course, you can use a more general nonlinearity instead of u to the power p. Okay, you put several more or less standard assumptions, and you see that this can be repeated and obtain solutions, a ground state solution for the equation with some sense and more general nonlinearity. Also, in case in which we have some symmetry, we can obtain solutions, infinitely many solutions for this equation. So now I'm adding the assumptions that F is an odd nonlinearity, and the result is that okay, there are infinitely many solutions with diverging critical levels. Again, for this, the proofs passes through okay, by using the symmetric mountain pass geometry for our functional, and then try to pass to the limit whenever lambda goes to 0. And in fact, I mean, it is possible to see that the divergence of the critical levels that we have whenever there is a lambda, this is maintained whenever lambda goes to 0. So in some sense, we can pass to the limit whenever lambda is 0. In fact, you can see the functional with lambda as a symmetric mountain pass structure. So we can define critical levels in the usual way. Okay, by doing the minimax function. There is a convergence whenever lambda goes to 0. I mean, the ground state level, the critical levels C lambda tends to certain C0. Okay, and this is done. And this is true for any J in natural number. There is a convergence also of the U lambda, of the solution U lambda, to some U0. And recall that whenever there is a 0, the parameter is 0, we are exactly for our equation, for our function. And U0 are critical points at level C0. And now, okay, it is proved that C0 with J, they are diverging. So we have diverging critical levels for our equation. This is a little bit technical, but at the end, the fact is that we need to compare our function, which has a lambda, with something which does not have lambda. A good choice is this one, this functional J. Then we apply again the symmetric mountain pass theorem to this functional J on a suitable manifold. And the manifold is the following one, is just the boundary of this set theta. The boundary of this set theta is basically the Neari manifold associated to J. And it is proved that J on this manifold satisfies the Palais-Smale condition, as infinitely many critical points and with critical levels. Okay, they are below C lambda, and then some sense by passing to the limit, we see that also C0, our critical levels, depending on J, are greater than the critical levels of J. This number Bj, so they are tending to plus infinity. This is more or less the moral of the proof. Just to conclude, I just cite here also the case where the problem is critical. So we have a nonlinearity u to the power 4. Okay, we are in R3 as usual. The assumption on F are again standard. In particular, in the hypothesis number 4, we need that F is greater than some power. The result is that there is again a ground state solution, at least when R this R which appear in hypothesis 4 is between 4 and 6, or otherwise C, the constant C has to be a little bit large, let's say. And the fact is that we want here that the Palais-Mail condition is satisfied. This is the reason we use this assumption on R and on C. Also here, the idea of the proof is to perturb the equation, but this time is sufficient just to do a perturbation in some sense, to add something to the left-hand side, okay, and show that we are under the condition of the Montempies geometry, that the Palais-Mail is satisfied under a certain level, and the Montempies level is there, so we can find a solution. And again, passing to the limit as lambda tends to 0, the solution is maintained in some sense. We get the ground state of our equation. So I think this is all. So I thank you for your attention.